the next example for proving any statement by using mathematical induction. Okay, then we see example here. Use mathematical induction to prove the formula Sn equal to 1 square plus 2 square plus 3 square plus 4 square, and so on. And then this one equal to m plus 1 and 2m plus 1 whole thing over 6 for all integer n greater than or equal to 1. So we use the 3 steps to prove, right? The first one, okay, the first one, we let n equal to 1. Have to prove the formulas are valid, right? Okay, then you have, so you replace s become s1, right? Equal to this one, n, right? Wherever have n here become 1 square. And then at the same time, you replace n in here too, n equal to 1. So become 1, 1 plus 1, and 2 times 1, so 1 plus 1, right? Divided by 6. So what we have, this one 2, this one 3 become equal to 6, 1 over 6, so equal to 1. So then this is correct because this one represent like when you have the n equal to 1, that means first term, when you sum it up, this one get equal to 1. But at the same time, they say for all the integer n greater than equal to 1. So if you replace, for example, right, from this case, if you can try if n equal to 2, right? So you replace it in here. So this one, S2, right, gonna be 2 power 2, which is equal to 4. Okay. So by the way, you replace this one, right? Replace this one, it end with a 2. So we have 2 plus 1. And 2 times 2 become 4. 4 plus 1 here become 5. Okay, replace n with 2 here. So this become 5 divided by 6. So you see that this one what we have. So become 3 times 2 becomes 6. 6 times 5 becomes 30 over 6. So we have 5. So you can check S2 means you're gonna sum with the first 2 terms, right? So then you see this one, first 2 terms in this one, right? So 1 plus 4 equal to 5. Yeah, that's correct. So you can try no matter how many terms, they say n greater than equal to 1. So if S3, that means you're gonna have equal to what the first 3 terms sum it up. The result will equal to S3. That's the one. Okay, so you can take this one work for all the integer n greater than equal to 1 up to n term. Okay, so that's this one. Then you see when actually this one, when you sum it up to Sn, right? Okay, they will equal to this one. This one like actually this one 1 square plus 2 square plus 3 square plus and so on to n square, right? This one actually equal to sigma Sn, right? Sigma n square, I mean, or sigma Sn, so equal to sigma n square. You remember last term, you learn, I give you the sigma. If we have this one, that sigma n equal to n plus 1 over 2, right? And then if sigma n square will equal to this one, okay, gonna equal to this one, n plus 1 and 2n plus 1 over 6. Okay, that's the meaning. If sigma n square and then sigma cube, right, n power 3, what we have is equal to, is similar to, we call this an odd number. You observe odd and this power 1, right? So this one gonna be what? Gonna be this one, the sigma n gonna be n and the n plus 1 and the whole thing here over 2. This is the whole thing, okay? This is the whole thing power 2. So actually this one means what? Means when you have sigma n power 3, you're going to have n power 2 times n plus 1 the whole thing power 2 over 4. That's equal to sigma n cube. Okay, remember this three formula I used to give to you, this one, when we learned last time, when we learned sequence series, that one. Okay, and then you still have to keep in mind, because this one in PAT question they like to give also. I remember if I give you up to sigma n4 and sigma n5, but n4 and 5 a little bit more. Okay, n4 similar to this one. Have the whole thing like this also, but increase another one more bracket here, and denominator gonna change. 6 become something else. The one. I will give you this one later. Okay, for this formula again. So if sigma 5 power 5, so it's similar to sigma n power 3. It's an odd number. So this will same exact like this one, but they're gonna have more term behind and the denominator more. So the idea, if you want to remember, just about here, and then again from this formula, I'll give you later. Okay, so they come back to here. Our proof continue. Our proof. Second one. Second step. Okay, so we have to get n equal to k. Okay, so you replace n with a k. So Sn equal 1 power 2 plus 2 power 2 plus 3 power 2 and so on. Okay, so plus k power 2. Okay, and then this one equal to, you replace all k here. The number k plus 1 and 2k plus 1. And the whole thing over 6. Third steps. Okay, let n equal to k plus 1. So no matter where have n, you replace with k plus 1. So become s k plus 1 equal, then you this time you just replace k n here, the last formula, because we need to prove. Okay, so you replace this one, replace in here. Okay, so become k plus 1 and then k plus 1. This one n become k plus 1 become k plus 2, right? And then this one you replace n. This one maybe have to write step by step. So k plus 1 plus 1 over 6. So now this one become k plus 1 times k plus 2. And this one gonna be 2k plus 3, right? Simplify it over 6. Okay, so then this one we have this. This is the one we need to prove. So this is the one we need to prove. Okay, so I wrote the third one here. So then we're gonna use the formula. You remember we have formula sk plus 1 subscript and k plus 1 is equal to sk, right? Equal to sk plus ak plus 1. Remember the formula? This is a k, okay? Plus 1. So what this gonna have? So you see sk, we have the whole thing is from here, right? Oh, this one should be sk. This one should be sk, not sn. Okay, so we have from here sk equal to this and this, right? The whole thing, and also equal to this one. So we replace this one. We replace this whole thing here with a sk. Okay, so because this one equal to sk here, you see that? This one, right? So this is sk. So you replace become k plus 1 and 2k plus 1 and the whole thing over 6 plus a subscript k plus 1. So you replace in here, right? Replace for the last term. Remember this term means the last term here. You replace n with k. So this one going to be k plus 1, the whole thing, power 2. Everyone get it? This replace this one, this term in this term. Replace it in, okay? So repeat, simplify. Simplify, you see this is LCM is 6, right? So we time this one. So we're going to have k and k plus 1. And this one 2k plus 1. 6 times, right? LCM, so become 6k plus 1. And the whole thing power 2. And divided by 6. Okay. Now, after this one, we simplify now. Become, oh, then you see what we can do. Instead, we're going to expand this one, right? We're going to get a common factor, k plus 1, because we try to get in this pattern. We want to get in this pattern, right? So we get k plus 1 out because we can get this one. See the one we need to prove, so we know what we should expand or how to simplify it. So now we have k plus 1 is a common factor. Here we have this one common factor here. Take it out. So we have left k inside and time 2k plus 1 plus 6 k plus 1 and close. And this one divided by 6. Now we simplify inside the bracket. So we have k plus 1 here. This one going to be 2k squared, right? Plus k. And this one going to be 6k plus 6, right? And the whole thing over 6. So what we have now, gonna k plus 1. Inside we left here 2k squared plus 7k, right? Plus 6. And then over 6. Then you see next one here, we can factor this one, right? So we have k plus 1. Factor this, factor it out, so become 2k. We need the middle term 7k plus 7k, so this one should be 2, 4. Yeah, 2 should be here and 3 here, right? So then this one 2k, this another k here. So this 4k, 3k becomes 7k, so this is a plus. Then over 6. So you see this one same or not? See this, the one we need to prove, we have k plus 1 here and 2k plus 3, yes, and k plus 2 over 6, yes. This one same, everyone. So we got this one, right? So from this side is what? It's a k, s k plus 1. So you see this, right? The whole thing here, same with the one we need to prove, they're equal. Okay, so that's the proof. So we can say the conclusion at the last, say Sn, just say this Sn equal to 1 square plus 2 square plus, or this one, just say this formula, okay? This formula is varied, right? For all of this one, for all integers, this is n greater than equal to 1 for all integers. Okay, so that's the one we prove. Okay, so we go next example. See next one.